Last time, we found ourselves in the midst of a paradox we call Gibbs paradox. We found that in the case of combining two systems and using a classical analysis, finding the classical partition function, taking the log of the partition function, and then ultimately trying to determine the entropy, we came up with an equation that was incorrect. And it was incorrect because we found that entropy with this formulation was not an extensive quantity. In other words, if I combine two systems with the same entropy, I didn't get a system that had twice the entropy, but the difference between the two systems by themselves and the combined system was 2n prime k log 2, where it should have been 0. So now we want to try to explain what happened, why this became a problem. Just a reminder, we calculated the energies of the systems, E prime and E double prime, on the basis of a volume V prime. So not a volume twice as large, just a volume the size of the system. Once I remove the partition, a molecule of either system could be found in a volume of 2V prime. Before we removed it, it could only be found in a volume of V prime. Let's look closer. Suppose the systems contain two different ideal gases. And now I remove the partition, and now I'm mixing two types of gases in this larger system. If I restore the partition, there's no way we could expect that the gases would unmix and you'd go back to the original configuration. So the entropy change in that case would definitely be 2n prime k log 2. No doubt about it. Those are two different gases. However, if they're the same gas, the same type of gas, and we mix them, and I can't tell one gas molecule from the other, which is the whole idea here, when I mix the two, it doesn't matter. The entropy change should be 0. It should be exactly the same. Interchanging one gas molecule from one side to the other doesn't result, or I should say, interchanging two of the gas molecules, one from one side to the other, doesn't result in a different state. So the entropy shouldn't change. So even though we have a system that is ostensibly classical before us, we can't treat it classically because the molecules are indistinguishable. That's going to ensure that we need to use quantum statistics as we move further, to get it right, that is. So if I want to make sure that I can use classical statistics, what I have to do is ensure that I'm not double counting states. And the way I can ensure that is to do the following. I take my partition function, and what I have, my real partition function is going to be the partition function I calculated, and I divide by n factorial. That will result in my not overcounting the number of accessible states. That means that I can write my real partition function is a one particle partition function, sigma zeta to the n divided by n factorial. That will give me the right answer. And so if I play that through, I do the following. I can say log z is equal to n log zeta minus the log of n factorial. I use Stirling's approximation to write out log of n factorial. So this is going to be n log zeta minus n log n plus n. Now notice the n log zeta term differs from the earlier term by these two terms, n log n and n. Now, since pressure and energy depend only on derivatives of log z, they're not going to be affected by this at all, so it doesn't matter. But the entropy is affected by that. My new entropy then, and this is correct, I'm not writing the wrong answer this time, is kn log v plus 3/2 log t plus sigma plus k minus n log n plus n, and that is correct. I can maybe shortcut that a little bit. Kn log v over n plus 3/2 log t plus sigma naught. And now if you're keeping score at home, sigma naught is actually sigma plus 1 or 3/2 log 2 pi mk over h naught squared plus 5/2 instead of 3/2. This is the correct answer. But we had to do it by making sure we inserted the 1 over n factorial to ensure that we don't overcount the states. So the question might come up, how can we be sure we are validly using classical statistics? And here's one way we might look at it. How can we ensure the validity of the classical approximation? Oddly enough, we have to bring quantum mechanics into this immediately. If I look at the Heisenberg uncertainty principle, delta P, delta H, greater than or equal to H bar, I have H bar over 2. H bar is fine for now. Let's apply this to a gas molecule or gas molecules in classical mechanics. So they have a mean momentum P, and maybe they have a mean separation of R. Classical description would be appropriate as long as P times R is much, much, much greater than H bar. As long as that's the case, classical statistics will work. It will be valid. Let's take that a step further. Equivalently, we could say if the mean separation is much, much greater than the de Broglie wavelength, classical considerations work. So this is good for classical, this is good for classical. Take it a step further. Our de Broglie wavelength, I can write as 2 pi h bar over the mean momentum, or h over p, mean momentum. So what this is saying is, if R is much, much greater than the de Broglie wavelength, the quantum description is equivalent to the motion of wave packets describing individual particles moving independently in a quasi-classical manner. Great, this is good. But suppose, on the other hand, my de Broglie wavelength, lambda, is much, much less than the molecular separation. So suppose is much, much less than that. That's, I should say, no, we already said that. Suppose it's the de Broglie wavelength much, much greater than molecular separation. This is a problem. Because the state of the whole gas is going to be described by a single wave function which can't be easily decomposed. So now we have correlations between the motion of the particles, even if there are no forces between the particles. Okay, let's do a for instance. So we can calculate a mean intermolecular separation if we picture each molecule at the center of a cube of side R. So I've got a cube of side R, and we put the molecule smack dab in the middle of that cube. I can say that n times R cubed would be equal to the volume, and therefore R, the mean molecular separation, I can write as V over n to the 1/3. Suppose I want to estimate the mean momentum. Well, p squared over 2m is about equal to the energy. And let's for one molecule, we'll write that as 3/2 kT. Or I can say that my mean momentum then is equal to square root 3m kT. And therefore, lambda, the de Broglie wavelength lambda bar, would be equal to h over square root 3m kt. So what this is saying, in order for the classical approximation to work or to be valid, it has to be that v over n to the 1/3 must be much, much, much greater than h over the square root of 3m kt. So what you're hoping is the concentration is very, very small. Or the temperature is quite high. Let's do a couple of for instances. Let's take helium gas at room temperature and standard pressure. Okay, so the pressure would be equal to 1.01 times 10 to the 5th Pascal. I like those units better than those bar things. Mean temperature, 328, right? Let's say 300 Kelvin, just make it nice and easy. KT then would be equal to 4 times 10 to the minus 21 joules. I can use the equation of state. N over V then is equal to P over KT. So N over V would give me something like 2.5 times 10 to the 25 molecules per cubic meter. And if I were to plug that in to get R bar would just be equal to 3.4 times 10 to the minus 9 meters. By the same token, if I take H divided by 3 mkt to find the de Broglie wavelength, I'm going to find a de Broglie wavelength equal to something on the order of 0.6 times 10, times 10 to the minus 10 meters. So notice in this case, it's good because R is much, much greater than the de Broglie wavelength. So classical statistics would apply very nicely to helium gas at room temperature and pressure. Okay, what about a case when it doesn't work? What about a case when the classical approximation fails? Let's look at, and we're going to do a unit on this later, conduction electrons in a metal. What we like to do is treat conduction electrons in a metal as an electron gas. And so, in fact, as an ideal electron gas. The problem that we're going to run into, though, is the numerical value of the significant parameters is going to be really different than helium. So in this case, the mass of an electron is 700 times, 7,000 times less than the mass of a helium atom. So that's a problem. More than that, if I want to calculate then the de Broglie wavelength, it's going to be much longer. In fact, it's going to be something on the order of 50 times 10 to the minus 10 meters. If I look at a solid as one atom in a cube, side 2 times 10 to the minus 10 meters, notice what I have. I have R is equal to then 2 times 10 to the minus 10 meters, and in this case, the de Broglie wavelength is greater than the interatomic separation. Therefore, the classical approximation is going to fail. And what we're going to need then is to use quantum statistical mechanics to be able to understand electrons in metals. So that's kind of an interesting way of knowing when you're going to have to use quantum statistics and when you can get away with classical Boltzmann statistics. There are some niceties about classical statistical mechanics, Boltzmann statistics. And that is, there is a validity also of the equipartition of energy theorem. This will work in classical physics. It fails miserably when we go to quantum statistics, but we can use this nicely for a classical system. So what I'd like to do is to talk about the classical equipartition of energy theorem. Let's consider the energy as a function of some f generalized coordinates. We'll call it qi, q1 through qf, generalized momenta p1 through pf, just the same old drill. E is E of q1 through qf, and p1 pf. F's the number of degrees of freedom in the system. Let's suppose we can split the total energy additively into a form like this. Suppose I can split it this way. I can write E sub I of P sub I plus E prime of Q1 to QF. In fact, we call this E1. Let's call this E1 and P1. QF, and then P2 to PF. Let's write it that way. So in this case, E1 involves only P1 and no other momentum coordinate or position coordinate. Secondly, suppose I can write an energy epsilon 1 for that one particle as B times P1 squared. So in other words, the energy is quadratic in P, P1. By the way, this could be any P. It doesn't have to be P1. It could be P2, Pi, P whatever. And where B is some constant. So the question is, what is the mean value of E1 in thermal equilibrium if the first two things are true? Let's say that the system is in equilibrium at some temperature T, which is equal to K times beta all to the minus 1. And I'm going to write then the mean energy, E1, as integral minus infinity to infinity, e to the minus beta, E of Q1 all the way through PF times E1, dQ1, dPF. All divided by the same thing, minus infinity to infinity, e to the minus beta, E of Q1 to PF, dQ1, dPF. Okay, it would be 1, except I've got that factor of E1 at the top, which is a bit of a problem. What I'd like to do is pull out the one term that involves E1 in the numerator. So here's the trick I'm going to play. I'm going to write this as integral minus infinity to infinity, e to the minus beta E1 times E1 times the integral minus infinity to infinity, e to the minus beta E prime, and that would be dQ1, dQF, dP2, dPF. Okay, so we're leaving out that integral. And this would be dP1 right here. divide this by minus infinity to infinity e to the minus beta prime dq1 df. What I get then these terms going away, and I'm left with only E1 bar is integral e to the minus beta E1 d E1 times E1 divided by integral e to the minus beta E1
Could you speak up, Dr. Close?
dP1. So I've got all that, I've been able to cancel all terms except this term. Well, that would be great, except there's, again, a difference between the numerator and denominator. I've got a factor of epsilon 1, or little e1 at the top. That should be epsilon 1, epsilon 1. Okay. Here's the trick. I can write e to the minus beta e1 times e1 as minus the derivative with respect to beta of e to the minus beta e1. Watch why that's a nice trick. Because what that allows me to do is to do the following. I can write E1 bar, my mean, as minus d beta of the integral of e to the minus beta E1 dP1 divided by integral e to the minus beta P1 all minus infinity to infinity. Notice this is just like saying minus the derivative with respect to beta of the log of integral minus infinity to infinity e to the minus beta E1 d E1. Which I can write then, and notice I can write minus infinity to infinity e to the minus beta E1 dP1 then as minus infinity to infinity e to the minus beta times b pi squared dpi. Okay, because we said we could write the energy in terms of momentum as a quadratic. Almost there. What I can say then, let's let y be defined as the square root of beta times p sub I. Watch what happens. My integral becomes beta to the minus 1/2, integral minus infinity to infinity, e to the minus b y squared dy. Which says the log of minus infinity to infinity e to the minus beta E1 dP1 is equal to minus 1/2 log beta plus the log of the integral e to the minus b y squared dy from minus infinity to infinity. But here's the great thing. The integral on the right-hand side doesn't involve beta at all. So I can say immediately E1 is just equal to minus d beta minus 1/2 log beta. Because this integral means nothing. If I play this through, of course, what I see is the mean energy E1 is equal to 1 over 2 beta, which I can write as KT over 2. Looks familiar. Mean energy, classical system. If I have, in this case, look at 1 degree of freedom, the mean energy is going to be 1/2 kT. If I have 3 degrees of freedom in one molecule, it's going to be 3/2 kT. If I have n molecules in 3 dimensions, it's going to be 3/2 n kT. It's beautiful. It's a very quick way to calculate a mean energy in a classical system. This works beautifully, only in classical physics, however. Quantum mechanics, things break down because you have a whole set of possible energy levels where the lowest energy level is E0, called the ground state energy, and you have higher energies that are more closely spaced, so you can't make approximations like this. But for classical physics, this is beautiful. What I'd like to do next time is do some examples where we can use, or applications of, the equipartition of energy theorem in classical physics. Thank you.